Okay, so before we hop into looking at jsrun, we've done enough of these training events to know that people want to have the presentations in front of them at all times. So Tom mentioned we have all of the material that we're going to talk about in the next 3 hours. 2 hours? 3 hours. Next 3 hours here in this repository. You can certainly just visit the GitHub site for it and view it here, but if you want the files, here's what we need to do. Git clone. And there's all your files. I'm getting a lot of blank stares like that's an obvious thing, but I guarantee you that there's somebody in here or somebody online that's not familiar with Git. So with that out of the way, I want to start by introducing jsrun. I guess I should maybe introduce myself briefly. So I'm Jack Morrison. I'm on the user assistance team here at the OLCF. And for the purposes of this event, that doesn't really mean anything to you other than we see all of the crazy things that our users try to do with these machines, right? jsrun is kind of a fundamental piece of using Summit, but there's certainly kind of this mysterious cloud that sits over jsrun because it was new with the Coral 1 systems, right? That's Summit here at Oak Ridge and the Sierra system out in California a little more. So jsrun, or job step run, was developed for these machines and can certainly be a point of confusion for people who are using our systems for the first time. Now, I think everybody in this room and everybody online is familiar with the Summit system, and at least familiar with what it is, right? If you're here and you're interested in the basics, maybe you're looking to learn about how to use it a little bit better. And I should say that you're not alone in that category. There are a few thousand users of this system, but there's a much smaller subset of those people that really know how to wrangle this machine and make it do exactly what they want to do. And I can't promise that you'll leave here today at that level, but at the end of the next hour, I hope that you're all at least a little bit less scared of jsrun and hopefully pick up some fundamental use, and if nothing, maybe some tools that can help you improve what you're currently doing with jsrun. So for a machine the size of a basketball court, I'm going to simplify it for a few minutes into something that looks like this. Right in the middle here, we have jsrun. And these arrows really represent kind of the normal job submission flow, how a user interacts with Summit. And if you're quick, you may notice that jsrun is the last piece of this. And we should probably talk about how we get there. So happy user, you over on the left of this diagram, obviously need to connect to the system. I'm going to assume you know how to connect to a remote machine, and we're not going to talk about SSHing to the system. But once you're on Summit, there actually is kind of an important intermediate step, which is the bsub command, which will launch a job. Rather, colloquially, we talk about it launching a job. Really, this is going to return to you an allocation of nodes. And when you submit a job to be scheduled and run on Summit, there are a couple of knobs at your disposal. There are a couple of parameters that are set at the allocation level, right? So at the jsrun level, at the jsrun level, you're specifying how you want to run a particular application. At the bsub level, you're specifying what you want your allocation to look like. So before we dive into jsrun, we actually need to back up and look at what options bsub provides us. Now, if you look at the IBM documentation, the quick line that you're going to see about bsub is that it submits a job to LSF. And that's true. But as I mentioned, really what this is doing is handing you back some compute nodes and moving your shell, moving your thread of control onto a batch node. Now, this is another point that if you're coming from another system or another center, or if you're unfamiliar with how we design our systems here at the OLCF, the concept of a batch node may be foreign. So we'll talk about that here in a minute too. So you can see this yellow host that I've introduced. It's a login node that is shared, right? Once you SSH to the system, you don't have exclusive access to the host you're on. You're sharing that with a number of other users. Anybody else who is logged in. And logins get load balanced across, we have 5 login nodes in front of Summit. Submitting a job, though, moves your process over to a batch node. You'll notice that anything you run under bsub no longer has a login hostname. It'll have a batch hostname. But jsrun is in the way of the compute nodes, right? jsrun is the gatekeeper to 200 petaflops, whereas bsub is your batch node, or is your gateway to a batch node. So when we look at using the bsub command to request an allocation, here's a short list of the things that you want to consider, at least when it comes to affecting your job steps that you will be launching, the applications that you'll be launching. So applied to every compute node at the startup time of the job are some options that you'll be specifying using the flag alloc flags. These are flags for your entire allocation. Among them are the CPU SMT mode. This is the simultaneous multi-threading mode. If you're familiar with, say, Intel processors, this is akin to hyper-threading. You can control with pretty good amount of granularity what you want each core on that processor to look like. The GPU multiprocess service, or GPU MPS, as you'll hear us talk about. This is a setting that is applied for every compute node and allows you to funnel, or I think about it as funneling multiple GPU contexts onto a single GPU. This will improve your ability, or rather remove your reliance on time slicing the GPU and allow multiple ranks to interact with the GPU at a given time using a single context. Additionally, we'll talk about the burst buffer on each compute node. This is essentially a 1.6 terabyte SSD on each compute node. And due to the nature of the hardware on that, it's not enabled by default. You need to request that. They have a limited read and write lifespan, so that's only available if you explicitly request it. And beyond that, there are other allocation flags that we're really not going to focus on today, but you should just know are at your disposal, right? Things like spectral you can enable, which is going to help you utilize the burst buffer effectively. Maximize GTFS is going to unlock some system processes and allow them to kind of absorb more of your compute node resources towards maximizing your management processes for the file system. And when you're specifying these in your bsub, either in your interactive, I want to phrase this. When you're launching a job with bsub, you can either do it in a interactive mode, right, where you're just command line interface, you're just using the bsub command, or you can submit a batch script in a non-interactive mode. We'll look here at the ways that you can specify multiple alloc flags together, but the important point, which again, I told you as a user support person, we see people mess this stuff up all the time. These are space-separated, quoted strings of options. People email us all the time saying, hey, why is this not running? And it's because you comma separated them. So looking at a non-interactive bsub, you're submitting a script, in this case, myscript.lsf. You see that with a single alloc flag, I'm only using one. I don't need to provide double quotes. There's nothing to space separate. So in this case, I will just be enabling the NVMe device, and I'll have access to that burst buffer. But really what I want to point out on this slide is that getting an allocation and running some command is not the same as running that command on a compute node. That's a really important point. If you get an interactive session, bsub, you have an interactive session, and you do /run my executable, you're not actually using a compute node. In fact, you'll be running on the batch node, right? We step back here. jsrun are the keys to the kingdom, and you'll be stuck running your application in batch node. You should think about jsrun as the only way to launch a process on the compute node. And you can see that here. If you were to just run the hostname command, it would return batch2 in this case. If you then run that under jsrun, right? Now we're telling it, hey, I want to run hostname on a compute node. You'll be, in fact, returned the hostname of the compute node. And then again, hostname without it, you'll be back on batch. The exact same example in an interactive mode. It's important to introduce vsub here. And I'm leaving these up in the slides as reference because when we go back through some of the hands-on examples, it'll be important to look at how we're specifying allocation flags and making sure that we're not running executables on batch streams. That's one of the largest things that we see as a support team of people coming from other centers. You try to run something interactively, but you're not immediately dropped onto a compute node. So now that we've kind of stepped through that workflow of reaching the machine, submitting a job, now we're all the way down to the point of using a compute node. So let's talk briefly about what a Summit compute node looks like. Now, this graphic we're going to be seeing a lot in the next couple hours. This is what a Summit compute node looks like to Tom and myself circa 2017. Because as we started supporting this system, we realized every time somebody asked about how to launch a job with jsrun, we would immediately go to our whiteboards and draw this graphic or something that looked like this and try to figure out what jsrun was actually doing. So this is by no means a technical spec of what an AC922 IBM compute node looks like. If you want to see that, you have the slides now, and I've linked the IBM Redbook so you can go read all the specs of the system. But for our purposes here, and from the perspective of a jsrun, this is really what a Summit node looks like. And it's a 2-socket node. At the top, in red, we have 3 GPUs per socket. We have 21 physical CPU cores, those are IBM Power 9 chips, on each socket. And then on each physical core, we have 4 hardware threads. And by default, that's that SMT4, that simultaneous multi-threading level 4. So, oh, and of course, we also have lots of memory on each socket as well. So that 4-way simultaneous multi-threading looks kind of like this. In 2-way multi-threading, you're further limiting the hardware threads on each core. So processes can only be placed in the first 2. If you were to specify vsub alloc flags SMT1, you would be further restricting physical cores to just the first hardware thread and only allowing processes to be placed in those first hardware threads. Down at the bottom, you'll notice that 1.6 terabyte burst buffer that I mentioned. We'll have I'll look at that a little bit later on in some of the hands-on exercises. And then a few other points that we have to talk about before we get into actually running jobs on this compute node. The first thing is that unlike a lot of other centers, if you're new to the OLCF, you have exclusive access to this node while you're running on it. You notice that when you submit a job with vsub, you give it the flag n nodes. It's the number of nodes that I want. You're not giving it n cores or n GPUs or anything like that. So it doesn't matter from the perspective of the center if you're using 1 CPU core and 1 GPU on this node. That's just you not using the machine efficiently, right? It doesn't, somebody else, some other user isn't going to swoop in and use the other 41 physical cores and the other 5 GPUs. Right? So you have exclusive access to this node while you're running on it. Service core isolation is also something that we do here. And if you were to look at the Redbook linked in that first bullet point and look at the actual technical specifications for this node, you would see that each socket actually has 22 physical cores, not the 21 that we have shown here. The 22nd core is something that we call our service core, or you might see it in our documentation as the isolated core. That is 1 physical core that is locked into SMT4, and we pack system processes on it that we don't want interfering with your end user application. Okay, so one of those might be, say, GPFS file system management processes that need to be running on the node. instead of letting that float, let the OS pick where it goes and float across the other physical cores, we lock it down, put it on the 22nd physical core of the node, and say our users won't have access to that. That helps reduce jitter in your applications, right? You don't want a heavy process that's not making forward progress, interfering with your science campaign that you're trying to run on the other 21 cores. That maximized GPFS allocation flag that I mentioned can unlock the GPFS processes and let them float around. But more about that in our documentation. And then the last thing I want to mention is the XBus. And you'll notice in the diagram here that this XBus sits between the two sockets, socket 0 and socket 1, and it's your only bridge between sockets. Now, we've intentionally left off all of the connections on this compute node diagram, right? If you're familiar with Summit, you may know that underneath all of this, you have things like NVLink, you have NVLink v2, you have very fast connections between GPUs and between CPUs. And we've intentionally left all of that off except for the XBus here. And that's because the XBus, as it relates to job launching and as it relates to jsrun, can actually be a bottleneck. It's to your benefit to think about the XBus when you're designing resource sets and when you're trying to figure out how to launch your application at the single node level. We'll see some more examples of that as we get closer to the exercise. Now finally, on to talking about jsrun. So as I mentioned, jsrun, or job step run, is what you can actually use to finally launch your application. Once you're on the system, once you have an allocation, once it's configured correctly, now I want to run my app. Now, one thing that makes jsrun tricky for folks who are new to Summit, or rather new to the Coral 1 systems, is that it introduces this idea of resource sets. And a resource set, if you're a Linux kernel person, is just a C group. That's how it's implemented under the hood. So as a user, you're effectively dynamically setting up C groups, which are truly just groupings of those physical cores of what GPUs you may want to use and some memory, which is maybe a bit of a special exception in Summit's case. So this is a way that you can shape a compute node to look how your application expects it to look, right? It's not maybe the most common system in the world to have a Power 9 processor with 21 cores and 6 GPUs tied to it. Maybe if you're coming from the world of DGX boxes, that's a familiar space. But if you're coming from the world of maybe this compute node has a single GPU on it, that can be a really daunting thing to try to figure out how to make your application then adapt to a node that has 6 GPUs. So in that case, you can kind of shape a compute node to look or appear as if you have more familiar nodes from the perspective of your application. It also allows for very, very flexible launching of your jobs. And Chris and Tom will get into this as we move into more advanced uses of jsrun. But just if some of the things that we're going to look at here seem like they're restrictive, just know that some of this, you can branch outside of this box. You can start doing really weird, highly customized things with jsrun as well. And they're also not as scary as they seem. We get a lot of support tickets, people asking about how to use jsrun efficiently. Hopefully by the end, we'll be able to talk about some tools that make this much less scary and much more approachable. Now there are some limitations to consider when designing resource sets. And maybe the first one is that they cannot span nodes. The largest resource set on Summit you could possibly have would be the 42 physical cores and 6 GPUs, which is one resource set per node. That's essentially saying, forget resource sets, use the entire compute node. And then beyond that, there's a condition. I mentioned that memory was a bit of a special case in resource sets. And if you want to access, pull back up here. If you are running on, say, socket 0, but you want to use all 512 gigs of RAM, you have to have at least one element in that resource set on socket 1. That is to say, if I were using, say, GPUs 0, 1, and 2 with just the first physical core in the top left, I would only have access to 256 gigs of memory for that resource set. But if I were to up that and request 4 GPUs, so now I have 0, 1, 2, and 3, now I suddenly have access to the memory on the other socket as well. That's a limitation that you might want to consider. But then again, that may also introduce crossing that X bus, right? You should then also consider that as a bottleneck. And then by default, resource sets are also homogeneous. So we will define a resource set and then scale up the number of resource sets. That's what we're going to be doing for the first hour here. As we get into more advanced uses of jsrun later, you'll see that you can actually have heterogeneous resource sets as well. Now, there are a few guiding questions for how, as we tell people, how do you want a node to look? There are a few guiding questions for this when you're trying to figure out what a resource set should actually look like. And the big one is, how does the code expect the node to appear? Is it written expecting that there's 2 GPUs available? Is it written expecting that you have 4 OpenMP threads interacting with 1 GPU? And those are all 1 rank 4 threads, 1 GPU. In the environment that you're coming from, wherever your code is run or it's been tested, that's maybe a good place to start. How can we make a Summit node, which is pretty flexible with jsrun, how do we make it look like a familiar environment? And then from there, create a resource set that meets those requirements, and then scale up to however many resource sets or however many nodes you need. This list will get you 90% of the way there. This list is what we tell pretty much every user that logs into Summit that they should be familiar with. And this is what we're going to cover in this first section here. So let's break this down a little bit. At the top, I have the kind of generalized format of what a jsrun line looks like. Obviously, we're invoking jsrun. That's the blue there. Skipping over to the green, this is our resource set definition. So how many tasks, how many MPI ranks do we want to be launching, right? What does our threading capability need to look like? How many GPUs do we need to use? Back in the red, how many of these resource sets do we want to run? And then ultimately, what program are we trying to launch? And any arguments that come along with it. So just going down the list here, I will mention that I typically use the short flags, and I will in this presentation, but luckily this essentials pack of jsrun options, the short flags are actually pretty intuitive. So N is the number of resource sets that we want. A is the number of MPI ranks that we're going to be running, we're going to be launching with, right? It's akin to like your --NP flag. C is the number of cores in a given resource set. G, the number of GPUs. B is your binding. So this is the number of physical cores available to a given process, right? If you're coming from a Cray environment and you're used to using aprun, you can think about this as being like a depth value, right? So we'll have some examples that investigate some of that behavior. Bind is a really important one. I should have highlighted that row there. Binding can get you into some trouble, and it's something to be aware of because we don't exclude oversubscription of the CPUs, right? So without proper binding, you might have 20 cores available and all your processes are packed on 1, right? And you have terrible performance, but everything looks like it might be right. Binding is probably where you've gone wrong. -R is going to be our resource sets per host. This is a flag that you want to keep in mind if you have particularly small resource sets. Again, we are going to explore the behavior of all of these here, but the default behavior on Summit is to pack resource sets into the fewest number of nodes that it can. If there's a GPU available and there's 2 CPUs available, and that's all you need for a resource set, it'll go ahead and fill a whole bunch of those. What this can do is actually leave unused compute nodes in your allocation, which directly equates to wasted allocation time. Nobody wants that. Latency priority is a way that jsrun tries to pick certain hardware to optimize the communication between certain things. Obviously, the flops on Summit are coming from the GPUs, and by default, we prioritize GPU to CPU communication. But this is also in the hands of the end user if you would like to change it. This is one that I would not typically recommend changing, but it is something that people occasionally would like to tweak. And then finally, launch distribution will affect the ordering in which you're starting processes within multiple resource sets. So if you have a single resource set, launch distribution won't do much for you, but if you're trying to change the ordering by which MPI runs are placed, this is a good place to start. So over the next couple of slides here, we're going to use this graphic that we are now familiar with and start building out a jsrun and looking at how these different options are going to actually affect the layout of your application. So if you just run jsrun with n1, you get almost nothing by default. But that's okay, because we have a lot of tools at your disposal to make jsrun line building and resource set design an iterative process. So with n1, you get almost nothing. Being explicit is to your benefit here. Explicitly requesting resources, also among the first thing that we tell users on Summit, is don't rely on the system defaults. Not necessarily because we're going to pull the rug out from under you and change a whole bunch of system defaults, but it makes your application launches and your job scripts much more human readable. Should you share them with support? Should you share them with your colleagues? And should you need to change a certain behavior, you can see pretty quickly what options you might need to look at first. So in the green here, again, we have our resource set specification. So we say we have one core, -C1, we have one GPU, and we're launching one task on it, right? And then we only want one of those, which is our N1 in red. So as I mentioned, the default behavior is to pack as many of these as we can onto as few nodes as we can. So how many of these resource sets can we fit in a single node? Well, we can fit 6. And that's because we're first limited by the GPUs. Sure, we have plenty of unused physical cores here. But since each of these resource sets has one GPU in it, we're limited first by the GPU. We can only fit 6. Now, what if we wanted to continue to build on this and utilize all of the physical cores as well? Well, then we can bump up the core count to 7. And now we have a fully utilized system. Or at least utilized in the perspective of all of the resources are in resource sets. But we only have processes on one core, right? And in particular, only on one hardware thread of one core. So what if we wanted multiple ranks? Well, in that case, we would increase our A value. And here I've also added the D packed, which is that launch distribution pack. And again, being explicit and including options is not going to hurt you. Dpacked is actually the default value. So I could have left this off and we would see the same behavior. And what that behavior is doing is taking the number of processes that you want to launch, so in this case, there's A7 per resource set, and filling a certain resource set before moving on to the next. Right? So if we were to switch that behavior to, say, cyclic, we now see instead of a column-wise ordering of processes, we move to row-wise, which is not really the appropriate way to think about it. Rather, it's resource set-wise ordering. So with a packed distribution here, you can see that processes 0 through 6 are all on resource set 0 in red, and 7 to 13 in the next resource set. Moving the behavior to cyclic, process 0 is in resource set 0, process 1 is in resource set 1, and then ultimately come back around and place process 6 in resource set 0. Do you have any questions at this point? This is the type of stuff that I talk about all day long. No questions. That's okay. So there's another behavior to launch distribution that I want to mention, which is a bit of a hybrid between the last two that we've seen. And this is a plain value. So this is akin to like a stride value. So by saying plain 2, I'm saying I want to use a cyclic distribution with a stride of 2. So you can see in the first resource set in red, we have processes 0 and 1. Whereas you then move on to the yellow resource set, and you have 2 and 3. Third resource set, you have 4 and 5. And in order to do this, you need to back down your core count, because necessarily the number of cores you have must be evenly divisible by your stride value. So I left this one in here because it's a good demonstration of how certain flags interact with each other. And jsrun will do a pretty good job of warning you when you kind of exceed its boundaries, when you have incompatible flags, when you try to do things that don't work out mathematically. But read the errors. Yeah, it's to your benefit to read error messages. But we also have some tools that can help you more easily visualize what's going on. Now, I've added a jsrun flag here that wasn't on our table, which is the -e flag, which allows you to specify environment variables that you want to pass on to your runtime. Now, you can certainly do this in your runtime environment. If I left out the -e flag here, and on the prior line I had export OMP numthreads equals 7, that would still be respected. But for readability here, I've just gone ahead and included it in the jsrun line. And you can pass any environment variable you choose to do it. So in this case, we have N2. We have 2 resource sets. We're launching 1 MPI rank per resource set, 7 OpenMP threads, so an OpenMP MPI application, BRS, so binding to the full resource set, -G1 for 1 GPU, and -C7 for 7 physical cores. Now, in this particular example, we have 2 compute nodes here, and you may notice that we are completely wasting one of them. This is why I mentioned if you have particularly small resource sets, that -R flag comes in handy. This is resource sets per host. So although we can fit 4 more of these resource sets onto our first compute node, and it wouldn't be until we included -N7 or increased what we have in green that we would ever not be able to fit these on one compute node, you can go ahead and add in a -R1 and push resource sets on over to another host. So, yes. Can you use the mic? Oh, thank you. Yes, thank you. So for those on the call who may not have heard, Tom was asking about the notation that we're seeing here in these graphics. So I did not mention this, thank you. Where there's an individual number, say in the top left, you see 0 on top of what would otherwise be a hardware thread number 0. That is a rank ID. That's a process ID. And then in situations where you have multiple threads, that you introduce this bracket notation. I introduced this bracket notation. So 0 sub 0 would be rank 0, OpenMP thread ID 0. Just below that, you would have rank 0, thread ID 1. And then onto the second resource set, because we have A1, we have 1 rank in this resource set, and then 7 OpenMP threads. So what we see here in this yellow resource set is rank 1, 7 threads distributed, 1 thread per physical core. And the same thing in this example, it's just shifted over to the second node. So that's kind of our basic toolkit. As I mentioned, that'll get you 90% of the way there. And to push you the rest of the way, there are either advanced jsrun options, which we will continue to look at through this afternoon, but there are also a number of tools at your disposal. It's kind of this jsrun toolkit. And this is a mix of things that we've developed here in-house that kind of targets the issues that we see from the users, kind of the sticky points, the things that are most difficult to work with, as well as things that are provided by IBM with jsrun. Now, the first one that I want to mention is a command shipped with CSN, which is the IBM product that jsrun sits within. And it's another JS command, it's a JS list. And this is going to show you job steps that are in any state, really, But this particular command, this jslist-r-d last one, is very, very helpful when working with job launch and when looking at resource sets. It's kind of a hidden gem. I always felt this a hidden gem of a command. What we're seeing in this output here is pretty much all the information that we were just looking at graphically, except for process placement. This is showing you that in the last jsrun command, so before running this jslist command, I'd run a jsrun. And you can see here that I had 2 resource sets, 21 CPUs per resource set, 3 GPUs, and in fact, here's the compute node it was on, and what socket it was on. It's very useful if you don't want to use one of our graphical tools, but you just want to do something quickly on the command line. JSList is your friend. And there are much more advanced things you can do with JSList as well that I think Chris is going to talk about a little bit later. I mentioned here, in this particular case, I'm looking at completed job steps. But if you were maybe you were running a couple hundred job steps at once and you want to see what's queued up, JSList will help you do all of that management as well. There's a useful tool called JS Task Info, which is provided alongside JSRun, and I believe the source is actually available too. If you inspect the installation of JS Task Info, I want to say that the source code is also available. But this is kind of a good first pass at Hello World for JSRun. It gives you kind of bare minimum information about what CUDA devices you have. It reads the CUDA visible devices environment variable. It gives you host names. In my opinion, it's maybe a little bit dense. It's not maybe user-friendly all the time. But it's something that is always available in your default path, right? So you don't need to module load anything. You don't need to compile anything. If you're just looking for a real quick look at, what is this JSRun going to do? JS Task Info is a good first go-to tool. I also want to mention that there are Spectrum MPI arguments that can be passed through JSRun. Particularly useful is the -GPU argument that, again, is quoted as a sub-option under --SMPI args. That's just to enable CUDA aware MPI, and I'll let you use GPU buffers directly in MPI calls as opposed to doing CUDA memcopy calls. So, yeah, I guess I'll leave it at that. This is one that we see people using frequently, but this is really to say that there are other options besides just resource sets that can affect the way you're running an application. Kind of in the way that we have alloc flags for bsub, there are SMPI args that you can list under JSRun as well. For more of those, I would point you towards the JSRun man page. If you've been to a few of these training events, you'll know that one of our go-to favorites is something called Hello JSRun. And this sequence of 4 or 5 commands here will bring in Hello JSRun into your environment, compile it for you, and get it ready to run. This is kind of like JS Task Info, but a little bit more user-friendly. It's designed by Tom here. It's made to run on Summit Dev and Summit and the other Power 9 systems here at the LCF. So it has been tried and tested on machines and is kind of a user-friendly interface for just on the command line, what is my JSRun invocation doing? And something I'm particularly excited to talk about is a new tool that we have. Folks in this room and the folks on the call are the first people to see this, so hopefully nothing breaks live here. Is a tool that we're releasing called Job Step Viewer. And this is what I've used for all of the graphics in this presentation. And it is actually a piece of software that is installed on Summit. All you have to do to use it is module load. And then you can run a JSRun command however you'd like. You can leave off the executable. You can provide an executable just like a normal run. So with no interruption to your workflow, it'll spit back a URL for you to go visit. And at that URL, you can kind of drill down into the machine and look at your process placement and see relative to other nodes, what is this node doing? What is that node doing? Am I oversubscribing hardware threads? And through that, we might throw some warnings at you. We might say, oh, hey, you're actually wasting your allocation if you were to run like this. Or, oh, hey, are you sure you want to run like this because you're not using any of the GPUs? You're leaving a lot of performance on the table. Okay? So I would highly encourage you to explore job step viewer. Of course, get in touch with us if you find bugs. But I expect that for anybody learning JSRun for the first time or trying to improve upon existing JS runs and improve how they're currently doing things, job step viewer will likely help you with that. So before we move on to questions, I'll actually demo this for you quickly if I can get an allocation here quickly, maybe while we're waiting in the queue. Oh, we have a reservation, don't we? Don't need to wait in the queue. So, well, maybe while this dispatches. Maybe I misspelled our reservation name. Well, yeah, there we go. Okay. So, minimal wait. I guess you still have to wait in the queue for a quick moment. I should also mention what I just did, if you're unfamiliar with using reservations. In addition to your usual vsub line where you're saying, oh, hey, charge my project, I want one node, give me an interactive session, you can add this -u flag. And we have a reservation for 36 nodes on the system. And it's just called jsrun. That's the name of it. You're not actually invoking the jsrun command here. And what that'll do is it'll run your job within that 36 node allocation, keep you from waiting in line with everybody who didn't decide to attend. So to show off job step viewer real quick, show you how easy this is to use. In module load, oh dear, the curse of live demos. What have I done? Oh, that's okay. Let's do this. So, yeah, I'm not sure why it's on me. Well, oh, did I misspell something? Well, this will work too. Well, so after you have a compute job and you load the job step viewer module, you can use jsrun as you normally would, and it'll return back to you a link where you can then look at Summit, drill down into an individual compute node, and see what that run looks like. So in this particular case, this was our jsrun command, and here's the graphic that is produced. This is what I used to make all of the slides, but this is also how the application would be launched on this compute node H31 and 14. Right? So very helpful to step through. That's correct. So the question was about the correct. The question was about the -u JSRun reservation. That's only good for the next couple of hours. So if you're watching this in 2021, hello, and that's not going to work. It won't even work tomorrow. Thank you, Ronnie, for pointing that out. So my point here is there are tools at your disposal to make this easier. Of course, you can always email us at the help team, and we will happily dive deep into your application and try to make things run as efficiently as possible. But there's also a good number of tools at your disposal to begin troubleshooting things yourself. So with that, how did I do? 148, not bad. Anybody have any questions at this point? Are there any questions on chat I'd be happy to address?
Quick thing. So would you say there is an advantage of using -r apart from what you showed? Is there any?
Interesting question. Can -r be helpful? So there are probably cases where it could be helpful. I will say what I typically see and where I would typically recommend using -r is to avoid wasting compute time. the example that I included, let's see, run back there real quick. Right here. This is the typical case that I see for using -r. Yeah. The correct approach would maybe be to say don't over allocate nodes. If in this case, in this run as it is, there's absolutely no need for a second compute node, right?
I mean, even if you had one node as well, you could push.
Not using -r. -r is resource set per host. If you wanted to, instead of pushing this green resource set, if you wanted to push that over to the second socket, you may first explore latency priority and see if you could do that using that flag. But beyond that, that's really where the power of explicit resource files comes in that we're going to explore in the advanced section later. Yeah, I mentioned that some of this, at least in the basics, may look like you're kind of locked into what you can do. But with explicit resource files, if you just want to use GPU 2 and physical core number 37, you can do that. You can slice and dice the nodes however you'd like. That's a good question.
So there was a slide you had, I'm not sure which one, but I'm sure there must have been where you had -a flag, right?
Yes.
I wanted to point something out to someone asked in the chat there. Sorry, the A flag in an actual example.
Let's see. This uses A. Is that sufficient?
Sure. So the question was about how MPI ranks are listed globally, right? If you think about it, seeing it, but oftentimes you see, say, A1 here, yet there's two resource sets, right? So you're not giving it, in this case, processes.
Correct.
And so typically you're doing that, look, using, you're not seeing the total number of ranks. The question is about how they're, are these numbered globally in that program? And that's
so there is a way, if you prefer to go along that line of thinking, there is a way to do that with jsrun that's maybe a little bit more familiar, which is to use the -p flag. And this is something that I guess I mentioned here, but intentionally didn't speak on. And that's because we typically recommend people who are trying to wrap their head around resource sets to use -a because it conforms to the idea of resource sets. But should you like to specify MPI ranks globally, you can do that using -p, and it will be a total number as opposed to a per resource set number. So you could run, ordering here, you could run this example, for instance, but instead of using -a1, you could use -p2.
so I don't recommend -a flags. I guess it does point out, though, that for people who aren't as familiar, it can be a little confusing. Yes, you can look at it as number of resource sets times however many MPI ranks.
That's correct.
And your program, although you may say one rank per resource set, 6 ranks per resource set, it will see the total number of MPI ranks globally. So if you had n to A6, that's 12 total MPI ranks that would be able to.
That's correct. Yes. Yeah. Thank you, Tom. Good clarification. Okay. Well, should any other questions come up, the Slack channel is not going away, at least for the next couple of hours. So please feel free to continue to ask questions in Slack if you're connected remotely, or there are a handful of us on the support team here in the room. Beyond that, of course, we're always happy to answer questions as well. Just get in touch with us. For the next section on our agenda here, we have some hands-on examples. And these are really designed to give you an opportunity to explore the options that we just looked at and explore the JSRun toolkit that I've talked about. Things like hello JSRun, or using job step viewer if you prefer, or exploring JS task info. Taking a look at these tools, using some of the basic options, both to dsub and JSRun. And if you're already familiar with these things, or you feel like you're already familiar, it's maybe a good opportunity to explore JSRun options that you're not currently using, right? So I would encourage you to pull up the man page, find something that you're not sure what it does, or you don't understand immediately what the behavior is expected. Try to use it with things like job step viewer or some of the other tools. And if you're still not satisfied, ask one of us, and we can collectively improve our JSRun knowledge in the next half hour. Sound good to everybody? Excellent. So the resources for the examples live under this basic subdirectory. And there's this basic examples markdown file. I'll go ahead and leave this up on the screen in here. But beyond that, I think we're just going to spend a little bit of time on Summit exploring basics. And then after that, we'll come back and dive into some more advanced topics as well.
Okay, so as Tom was saying, so what we're going to do is go into some of the tasks that Jack kind of mentioned earlier, maybe in just a little bit more detail, just a couple of the topics. So I'm going to go over a little bit of how to run multiple JS runs within a single batch allocation. And Tom's going to go in then into the ERF file in more detail. So mine will be shorter, and we'll spend a little more time on the ERF file. So jumping into this, so JSRun gives us the ability, JSRun I should say, in its underlying CSM configuration and tools, gives us the ability to launch multiple JS runs within a single batch allocation. So because the underlying CSM knows of the allocation that you've been given in the batch script, as well as it also controls which JS runs, where they run. So it knows what you have and what's running. So it gives us the nice ability to simply say JS run and let it run, and then launch another JS run and let it run on separate resources that are inside your allocation. It gives us the ability to run multiple JS runs both within a compute node that you've been allocated and across nodes that's within your allocation, and you can mix them as well. So when I think of this, I kind of think of two separate kind of high-level methods of running. The first is a sequential method in which all the JS runs that you launch separately. So the first JS run will run. The next JS run will not run until that first one completes. So it's kind of the first JS run runs, the next one, once it completes, the next one starts, and then the next one. So it runs through that way. So in that method, you're running multiple JS runs, but they're not running at the same time. The next way is simultaneous. So in this method, we're running multiple JS runs at the same time. So in this way, if I launch 3 JS runs, I could do it in such a way that all 3 would run at the same time. And we would let the underlying system that we're talking about control and make the layout and placement and make sure that those are not running on the same resources. So something to think about, because these jobs can only use what they've been allocated by the batch system. So it's important to keep in mind how the jobs run and how many resources that you need to request to ensure that there are resources there to run the jobs as you hope. So the first thing you need to make sure that you get enough nodes allocated to run the job that you're looking to run. So under the sequential method, because the jobs run not all at the same time, you run one JS run at a time, you need to make sure that there's enough nodes to run the largest of those JS runs. So because those will reuse resources as they're free, so just make sure you have enough to run the largest of the JS run. Kind of the flip side, when you run the simultaneous, when they all run at the same time, you need to make sure that you have enough resources to launch them all at the same time and launch them on separate resources. So in this when you run simultaneous, you need to kind of get the sum of all of those simultaneous JS runs, all of the nodes that those will require. You need to kind of add them up, and that's the number of resources that you'll need to ask for. And then going back to wall times, the other thing that you'll need to make sure that you request, sequential kind of goes the other way. Because everything runs back to back to back, you'll need to make sure that you have enough to run the sum of all of those needed wall times. So you need to have enough wall time with some buffer to run the first all the way to the last. And then we'll go the other way for sequential. Because they all run at the same time, your wall time really only needs to be as long as the longest running JS run in that group. So next, I want to go through some of the sequential and the simultaneous, and kind of show what they look like in a batch job. So this is a batch script. You can see at the top, it asks for the resources, and then at the bottom we have all of our JS runs. So in this example, kind of just to show what the example, the first JS run is kind of a series of JS runs. So we have a.out, and it runs with an input file, a file A, and then we do some post-processing. File A, maybe file A is used to create file B, and then we run an a.out with file B as its input deck, and then we do some post-processing, and we run along the a.out with that input deck that we just created called file C. So in this method, the first JS run will run. The second JS run will not run until that first JS run completes. Once it returns, the next job will run. Once the first job completes, the system will also free those resources, and then the next job will maybe take some of those resources and run. It'll free the resources, and then so forth and so on. So this is kind of a basic example, just to kind of show what a sequential, when I talk about sequential, what it looks like. So just to kind of further show the example. So when we look at how much time to grab in the batch job and how many nodes to grab, this is a kind of an example, just so that first task will need, it has 6 GPUs, so it's going to need 2 nodes. And let's say it runs for 25 minutes. When it completes, the next process will kick off. It's short. It only takes 5 minutes, and it's only asking for 4, so it's really just a piece of a node. When it completes, the next will run. So we'll say this one needs 30 minutes. It's a little bit longer than the first. It still needs 2 nodes, and it can reuse those same 2 nodes because they've been released by the previous processes. Once it completes, right, it'll release those resources and run the next post-processing process. And again, this only takes 5 minutes, and then just a piece of the node. And then our final job only takes, or final JS run only takes maybe 25 minutes, and it needs a full 2 nodes. So when we look at how much we need to ask for in the batch script, what we can do is say, because these are running back to back and they can reuse the resources, we just need as many nodes as the largest JS run. So the largest JS run in this case is 2, so we'll ask for 2 nodes. Now, because they run back to back, we need to make sure we have enough time to run from start to end. So if we add up all of the run times for all of these, we get 1.5 hours. So we'll add a buffer in there and request a 2-hour wall time. All right, so that's sequential. And now a quick example of simultaneous. So in this example, say we figured out how to create our input decks, file A, B, and C, in another method outside of the batch run. So now these jobs, we have the input deck we need. They're not tied together, so we can run them all at the same time for this example. So in this example, what I did was take the same JS run commands that we ran on the previous slide, but I want to run them all at the same time. So the method I used on this slide is using the Unix background. So you can see the background command at the end of each JS run. So basically what that'll do is run the JS run, place it in the background, and return so the shell can run the next command. Once it's in the background, jsrun and CSM will control where that job is placed, and the shell will move on and execute the next command, which CSM and jsrun will control the layout. They know where the previous job has been placed, so they'll place these on additional resources that you have allocated to the batch job, and the same thing for that last JS run. Now, one key piece here is the wait. So you must add this. This is just a Unix wait at the bottom of the script. This tells the shell, right, to stop and wait on all the background processes. So don't execute, don't move to the next step until all of the background processes have completed. This is a key piece. If you forget this, then the shell will happily background all your tasks and then hop out, and you will have waited in the queue to run nothing really. So, so if we look at how much time we're going to need for each of these, we run through the same syntax here. We say, all right, these are the same tasks we ran before. So we know the first task needs 2 nodes. It's going to run for 25 minutes. The next also needs 2 nodes. It's going to run a little longer for 30 minutes. The next will run for 25 and still needs 2. So since these will run at the same time, we don't need to add up the wall time in this case. We can take the longest, which is 30 minutes, and then we can add a buffer to it and ask for an hour, and hope, knowing that it'll complete under that hour, but at least we won't hit the wall time limit. For the nodes request, what we will need to do, though, is make sure that we have enough nodes to run all of these at the same time. So we'll add up the resources and allocate six nodes. All right, so that's one way to run the simultaneous method. So jsrun gives us another method. This is the ---- immediate, or the little case is -i. Basically, what this is very similar to the background. What this does is tell jsrun to go ahead and add this jsrun request to its queue, and then move on to the next command. So kind of very similar to running it and throwing it in the background. So you can, very similar, instead of adding things in the background, you can use the immediate and let jsrun queue them and move to the next step. Similar to the wait, you'll have to add at the end the JS wait. JS wait gives you a little bit more abilities. You can say JS wait all and wait for all of them to complete, or you can say JS wait and give it an individual one. I guess that could give you the ability maybe to script some order. But if you just want kind of a similar background and wait for everything, then JS wait all is what you need to add at the end. And I've given an example here in the black box of what we just talked about: jsrun and then adding it, throwing it in the background, and then adding a wait. You can see the next line. We jsrun, and we used our -i to say immediate, and then we did JS wait all to wait on that. An important note, though, about the immediate flag, by default, all of the standard out and error will go to dev null. So that is the default. If you don't want that to happen, then you'll need to use the JS runs ---- IO standard out, standard IO standard error, or the shorthand -o and -k to change the location of the standard out and standard error. And you can see an example that I ran. I included the output files and show you can cat them, and it's got the same output that we did before without the immediate, where it went straight to the standard out to the screen. On a side note, also, if you specify a file that the system can't open, the default behavior is to send that to dev null as well. So if you get in any cases where you're looking for outputs, this might be what's happening to you. Okay, so we talked about the JSRun queue. And Jack mentioned JSList to see what JSRun is doing. You can use JSList also to look at this queue. So basically, I mentioned earlier that JSRun and IBM's underlying CSM will take care of the placement. It knows what you have, knows what's running, it controls where things are running. So basically what JSList gives us the ability to do is query that queue. And so you can query the queue. I think Jack gave some flags that you can just give JSList. What I wanted to show here is how you would do this if you're in an interactive job, then run a bunch of JS runs, throw them in the background, you type JS list, and you can see your list of jobs that are running, what's completed, what's queued, and it gives a little bit of information about what those resource sets look like, the number of GPUs and nodes and such there, exit status. But you can also, if you want to see this from outside of an interactive job, say you submit a batch script and it starts running and your JS run is in the background running, you can tie into that. If you do so you submit it. An example here shows you do B jobs, you give it the job ID and disk rep for your CSM allocation. And then you can run JSList from the login node of Summit or Ascent and give it the CSM ID, and you can see what your job's doing in the compute node. Okay, so my last slide, everything I've given so far has been an easy, good fit, which is probably maybe what you want to do. But if you don't, if you have a workload that doesn't fit necessarily neatly on the resources that you have, I wanted to give this slide to kind of show what jsrun CSM will do if you give it a request that won't fit on the resources that you've been allocated. So in this example, I grabbed 2 nodes in an interactive job. I run a jsrun that grabs 1 core and 6 GPUs, and that begins running because I throw it in the background. It can start running. It grabs on the first node. The next job doesn't grab any GPUs, but it grabs all of the cores on the node, throws that in the background. That can run because you have 2 nodes, so that's placed on the second node. So what we have now is a job running on the first node with all the GPUs and a job running on the second node with all the cores. Now we try to run a JS run that's really small. It just needs one GPU and 1 CPU. But because we can't run a resource set that spans nodes, this job will not fit, right? Because there's not enough nodes, there's not enough GPUs on the second node, on the first node, sorry, to fulfill this request. There are plenty of cores there, but not enough GPUs. On the second node, there's plenty of GPUs, but not enough cores, so there's no place for this job to run where it can fulfill a resource set on the same node. So what the system does is just queue it. So you can see I run these and I ran the JS list, and you can see the first 2 jobs are running. You see kind of what they're using, and you'll see the third queue. And that's kind of an easy way to, if you want to play with this, grab an allocation and see what it looks like. For just quickly to mention, what I use to see where things are running and place them and hold those resources for a little bit, I use the JS task info that Jack mentioned earlier. So that gives us a little bit of information about where the job has been placed. And then in that same script, in that same shell that I launch the JS task info, I simply run a sweep. So what that does is print where you are, and then it holds those for enough time that I can launch other JS runs and see what the behavior would look like, say if I ran a job that was actually doing compute and taking up a little bit of time. So just kind of one way to do that. You can also grab the hello test that Jeff mentioned earlier and simply add a sweep at the bottom of that C code, compile it, and it will print more information than this and do the same thing at the end of it. It'll sleep before it returns and give you the same functionality with a little bit more detail on where that job is being placed. All right, so that is task in the multiple jobs, and I took a little bit more than the 10 minutes that I had, but I'll turn it. All right, I'll turn it back over now to Tom. And if there's any questions.
Okay. All right, so my name is Tom Papatheodore. I'll be talking about the explicit resource files, or ERFs. I always want to call them ERF files, but it's already sort of baked into the name, so I'll try to refrain from doing that. So before getting started with this, I wanted to point out that this is sort of a new functionality to jsrun, so all of the bugs probably aren't worked out yet. I know I ran into a couple issues while just creating these slides, so I would encourage you, if this is something that you need to use or that you have a use case for, to start using it, and if there are any issues, submit those to the OLCF help email, and then we can pass that information on to IBM to start trying to harden this functionality. Okay, so what is an ERF? These are these explicit resource files that allow you more control over defining your resource sets and the processes that have access to those resource sets. So you can do things like create heterogeneous resource sets. You could use multiple executables in the same job step, so MPMD mode, for instance. And just generally gives you more fine-grained control over mapping your processes to the hardware threads that are in your resource sets. So taking a look at the basic syntax, at the highest level, these files contain a preamble and a body. The preamble lets you set options that influence the whole job step. So things like the way or the order which processes are mapped to your resource sets, or either among or within your resource sets. If you want to allow CPU oversubscription, or you can specify, say, the executables that are run within the resource set. So these are the type of options that you can set in the preamble. For the body, this is where you actually define the resource sets and the processes that have access to those resource sets, as well as the binding of those processes. So the preamble, there's lots of options that you can use in this preamble. We're only going to cover 2 of them here, but there's a link down at the bottom there where you can look at the full list of these options that you can set there. So, but it contains things, like I mentioned, similar things that you can do in with jsrun. So like the -d flag, for instance, right, which is your launch distribution. You can do things like that within the ERF. So we're going to look at these 2. So we'll look at the bottom one first. So this app option, this allows you to define the executables that you want to run in your job step. So you might have, for instance, app0 and then a.out and some arguments. And then you may have right below that app1 and :b.out and its arguments, right? So you can define these apps. And we'll take a look at an example on how you'd actually do that later on. The CPU index using, this lets you set whether you're using logical or physical CPU indexing for your hardware threads. And I always have this set to physical. By default, this is set to logical. But I would encourage you to use physical for the following reasons. Or maybe not for the following reasons, but this is the difference. And I'll try to point out why we do that. But so this is a Summit node that we've seen already. Physical indexing in this case labels these hardware threads in the order that you would expect, based on knowing that there's 22 physical cores on each of these sockets, right? Let's see if I can make a laser pointer here. Okay, right. So if you have 22 physical cores, each with 4 hardware threads, you would have 88 hardware threads on each socket. So you would expect this to go from hardware thread 0 down to 87. But as we've mentioned, there's one core that's been isolated and so isn't available to you. So that's why 84 through 87 is missing. And so if you then, when you jump up here to this next socket, you start at 88, right? And so it's physical indexing in the sense that you're numbering these hardware threads knowing that there's actually this physical core down there that's missing, right? As opposed to logical indexing, where you would just skip by that missing port and start labeling these at 84, right? So it labels them according to the hardware threads that are available on the system, not what's physically there. So that's the difference. But all of our diagrams like this, right, are all labeled with physical indexing. And so if you try to use logical indexing, there may be reasons you want to, and if you do, you can do that. But if you want to follow along with these sorts of diagrams and the tools that we have, they all use physical indexing. So I always include this flag with a value of physical. And there's actually a GitHub OLCF tutorials that we have with several tutorials in it, but there's one specifically talking about CPU indexing in it if you want more information on that. Okay, so after the preamble, you'll have the body. So as I mentioned, this is where you define the resource sets and the processes with access to those resource sets. You can write these in different ways, and we'll look at that. But in general, this box in the middle shows you the common structure that you'll follow. So you have this process specification, colon, and then inside of these curly braces, you have this resource set specification. So as the names imply, the process specification is where you specify which processes will have access to the resource set that you define to the right of that semicolon there. And we'll look at how you bind processes on this side of the semicolon to the resources on this side of the semicolon in a couple of slides. So process specification we'll look at first, and this is something that can be accomplished in two ways. So you can do what's called specific process specification or process per resource set specification. Kind of mouthful. So for the specific process specification, you're doing what the name sounds like you're doing. You are defining which specific processes have access to the resource set over here, right? So you're saying rank, colon, and then processes. So you're defining which specific processes. So here, we're saying rank 0, 1, and 3 are going to have access to the resources over here, right? And so this processes, as you can see here, you can have this comma-separated list, or you can have a range, say it was 0 dash 3 or something, or both to define those processes in that list. For process per resource set specification, instead, you're just giving a number of processes or ranks that have access to the resource set. So here, for instance, you just say 6. You don't say which specific processes, you just say 6, and that's what's going to have access to these resources. To define the resource set itself, you'll use a semicolon separated list of key value pairs. So here we have key 1, colon, and then its value, and then a semicolon, right? Key 2, its value, and a semicolon, and so forth. And we'll look at what some of those keys can be. So host is the first key we'll look at. So this lets you specify the hosts or the nodes where the resource sets will be created. So the values can be a comma-separated list and or a range of host identifiers numbered from 1 to the total number of nodes in your allocation. So you can also use an asterisk to say I want all nodes in my allocation to create these resource sets. And although the documentation by IBM shows that 0 is a acceptable number, on Summit, 0 represents the batch or launch node, which you don't have access to with these ERFs during the job step. So that's why I say up here, just starting from 1. CPU. CPU is the key that you use to specify the hardware threads you have access to. So the value here is actually, you're going to specify a set of hardware thread groups. Okay, so that will become, hopefully that will become clear here as I continue. So right, the values, or these sets of hardware thread groups, are defined as a comma-separated list of hardware thread groups, where the hardware thread groups can be defined as comma-separated lists and or ranges of hardware threads. So this would be a group of hardware threads, right? It has a list, comma-separated list, as well as a little range in it. So you can do this. So this group would contain hardware threads 0, 1, 2, 3, 5, and 7. Okay? And before moving on, I think I should probably say that these groups, this set of groups, is going to be a comma-separated list of these type of groups, right? So here is a set. You have, here's a group of hardware threads, comma, another group of hardware threads. And the point of doing this is in maybe 2 slides, you'll see that you're mapping processes or MPI ranks to those groups of hardware threads. And that's why you separate it in this way. So you have this set of hardware thread groups because you're going to have a set of MPI ranks that need to map to those. So you can do this comma separated list as we saw here, or you can give a starting hardware thread ID and then a depth of hardware threads. So in this case, 0:4 would mean hardware threads 0 through 3, right? Because you start at 0, you have 4 of them, it would be 0 through 3. So you can define it in different ways. But this method can differ based on the SMT mode that you have, right? So if you give a depth of 4, you have SMT mode 4 versus 2, it's going to make a difference on which hardware threads you actually get. Right, so these 2 methods can be mixed within a set of hardware thread groups. So here you can see you have 0, 2-3, and then you have this depth method over here. And so within the set, you can use both of these, but you can't use both of those different methods within a group of hardware threads like you do here, right? So here we have a starting hardware thread ID and a depth, and then trying to do this list as well. And so you can't do both those within a group, but you can do it among groups, if you will, right, within the set. And you can use an asterisk to specify that you want to use all hardware threads on a node, if there's a situation where you want to do that. So the last 2 keys we'll look at, we have GPU. So this specifies a group of GPUs. And I would point out that all processes with access to a resource set have access to all of the GPUs in that resource set. You're not binding processes to GPUs the way that you're binding processes to hardware threads within the resource set, right? That's something that you would need to do programmatically in your code, right? CUDA set device ID or something like that. You can use an asterisk to specify all GPUs in your resource set. The memory option I'm not actually going to cover because it's not available on Summit. So it is an option in LSF, and I put it here so that I at least remember to point out that it's not available on Summit. Okay, so now let's look at that binding. So the processes that are defined in that process specification section are then bound to the groups of hardware threads in the resource set specification section sequentially. So for the specific rank specification method, where you're saying ranks and you're giving the actual specific rank IDs, you can see that they're mapped sequentially. So you have rank 0 would map to the first group of hardware threads in your set, right, where this whole thing is the set. Rank 1 would map to the next group of hardware threads in that set, and so forth, sequentially, right? So just to point out here, generally, host would be a key, right? And then 1 would be its value, semicolon. CPU would be a key, and then this whole set of groups of hardware threads here would be its value, and the same thing for GPU here, right? So key and then its value over here. And so for the process per resource set specification, which is a different way of specifying those processes, you would just have that 6 there, right? So you're saying 6 ranks have access to these resources. And so although it's not explicitly, ordered like this is, to where you can do this sort of mapping back and forth, what you do is you can think about the node local ranks being mapped to the groups of hardware threads. So node local rank, if you're not familiar, what I mean by that is just, let's say you have 12 MPI ranks, where you have 6 MPI ranks on each node, right? So globally, those would be called MPI ranks 0 through 11. Yet on each node, they would be labeled 0 through 5, right? So they have a node local ID. So node local rank 0 would have access to this first group of hardware threads in the set. Node local rank 1 would have access to this group of hardware threads in the set, and so forth. So this is how this is how you actually bind the MPI ranks to the hardware threads. You simply have this list, or this set, where you have one group of hardware threads per rank that you have defined. Okay, so how do you actually use an ERF if you've defined it? To do this, you pass jsrun the --erf underscore input flag and give it a file name or a path to your ERF, like we see here, followed by your executable and its arguments. As we'll see in example 3, you can actually define the executables that you want to run inside of your ERF itself, and so in that case you wouldn't pass it an executable since they'd be defined in the ERF. And it's also possible to create an ERF by using the --erf underscore output and giving a file name, and it will actually output an ERF for you based on the normal jsrun command that you ran. Bill, you look like you have a question.
I didn't know if you were, I was waiting for your next slide to see if you said something.
Ask, I'll tell you if it's there.
Well, I was going to point out that per your discussion earlier, that last example, one thing to be alert to is it will default to the logical CPU indexing. So that may confuse you when you then look at the resulting file.
I was not going to bring that up. That is a good point. Yes, when you output, yeah, it's going to give you logical indexing. Thank you, Bill. Okay, does anybody have any questions before we look at examples? These examples are also supposed to meant to sort of clear this up a little bit as well. So maybe you'll get some of your questions answered during the examples, but if you have questions, ask them now as well. All right, if anyone sees any questions coming through from the remote folks, let me know. Okay, so in these examples that I'm going to show, assume that you have the following interactive allocation on Summit. So I've requested 2 nodes. The cores are in SMT4 mode, so you have access to all hardware threads. And I've enabled CUDA MPS using this ALEC flags, GPU MPS. So that's not necessary really for the examples that I showed, but in case people try following along, some of the tools might need this MPS if you're going to try to set up a configuration where you're having multiple MPI ranks talk to the same GPU. And so you can do this. You can request the same allocation either now or during the exercises, the hands-on session, using this bsub command, where you'd obviously have to replace this project ID with a project that you are associated with. Also, during this tutorial, we have this reservation of 36 nodes. So if you want to pull your nodes from that pool of nodes in that reservation, you can use the -u jsrun flag to pull from that reservation, but only during this tutorial. And please don't let that jsrun confuse you with an actual jsrun command. Perhaps that's named poorly. Okay. So here's an example. Going to be some examples here that are you could do with a normal jsrun, just to sort of show you the difference and understand the syntax, make sure everybody understands. So here we have a diagram from Jack's new tool, which is very nice. And so this shows that we have 6 resource sets on a single node. Each resource set contains 7 physical cores, or 28 hardware threads, and 1 GPU, right? So this red resource set has hardware threads 0 through 27 and GPU 0. This yellow resource set has hardware threads 28 through 55 and GPU 1 and so forth. And then there's 1 MPI rank that has access to each of these resource sets, basically, right? And all of the resources in that resource set. So 1 MPI rank has access to all of the physical cores in here. And so it can do things like spawn open MP threads on it, And so in fact, that's what we've done. So remember this notation with these square brackets shows outside of the square bracket to the far left, that's the MPI rank ID. And then inside of those square brackets is the OpenMP thread ID. So MPI rank 0, thread 0, MPI rank 0, thread 1, MPI rank 1, thread 0, MPI rank 1, thread 1, so forth. So if you wanted to do this with a normal jsrun command, you would say jsrun, you would give 6 resource sets. Each resource set has 7 physical CPU cores, and each, okay, I didn't define it here, but you have 1 MPI rank per resource set with the -A1. And then each of those ranks has access to all 7 physical cores in that resource set. That's what this bpack does. And then 1 GPU. And so this here is just showing the text output from running the Hello JSRun tool. I've cut out the center here just to make it fit on the page, but it's the same output that you would see over here. It's just in text form. Okay, so this is what you do with a normal JSRun, which we're not interested in at the moment, I guess. We'll move on to ERFs. So this is how you would do it by defining the process per resource set specification. So you would say, you would define 6 resource sets. You would say this first resource set on this line has access to hardware threads 0 through 27, right? Because we've said starting hardware thread 0 with a depth of 28. So that gives you hardware thread 0 through 27. And GPU 0, I want this on host 1. I have 2 hosts. Host 1 is where I want this. And I want 1 MPI rank to have access to this resource set and be bound to those cores, those hardware threads. My next resource set starts at hardware thread 28 and has a depth of 28 hardware threads, so that would be 28 down to 55 for the hardware thread IDs. It has GPU 1 in it. It is also on host 1, and there's 1 MPI rank that has access to that. And then so forth for the rest of these. I won't go over all of these. And if you run it, setting OMP num threads to 7, like we did in the previous example that I didn't mention, and then run this, so you have this --erf input, and then the file name, and then run the executable, and then I've sorted it as well so that it has nice output, you would get the results that you see here in text, and this is the results that came out of it from the job step viewer. So it's the same thing we had on the previous page, we've just done it with an ERF instead. And then here on the next slide, I show how you would do that with specific rank specification. It's really the same thing, so I won't bother going over it, but here you can see I have the specific ranks as opposed to just a rank, right? So that's really the only difference, but that's how you would do it. And it gives you the same output. Okay, so looking at another example, here we have 2 resource sets. We have 1 resource set per node, where each resource set contains 6 physical cores or 24 hardware threads and 6 GPUs. And then there are 6 MPI ranks that have access to each of these resource sets. And each of those MPI ranks has a depth of 4 hardware threads. So here's MPI rank 0. It has access to these 4 hardware threads. Here's MPI rank 1. It has access to these 4 hardware threads. Over here we have rank 8 with these 4 hardware threads, and so forth. So something I would point out here is when you're talking about JSRun in the normal sense, you're typically thinking about physical cores when you're requesting, like -C, for instance. Or even like the binding, right? Talking about -B packed :7 or something. But when you're talking about ERFs, you're typically thinking in terms of hardware threads, right? And then thinking about how that corresponds to the physical cores. You're defining the hardware threads, so different way of thinking about it. Right, and so if we set 1, since this code uses OpenMP, I set threads to 1, and then I run this, 2 resource sets, 1 resource set per node, 6 physical cores per resource set, 6 GPUs per resource set, 6 MPI ranks that have access to the resources in those resource sets, and each rank has access to 1 physical core. And then I run it, and it gives me this output down here in text, or this result up here from job step viewer. So this is what you would do with a normal JSRun. How would we do that with an ERF? Something else I should point out real quick is that this layout of where these CPUs ended up is just the default behavior of JSRun. I didn't explicitly say, I want these 3 ranks to land on these physical cores, right? These ones and then jump over to the second socket. That's just what it does by default due to the latency default that is set there. But with the explicit resource file, you do tell it exactly where it can land. So I could have had it land, one of them land down here if I wanted, and just be out of the rest of the order that we have here. Right, so this is what the ERF would look like. As always, I've put in the CPU index physical. And so I've done this in one line by saying, okay, these are the hardware thread groups I want. I want hardware thread 0 through 3, 4 through 7, 8 through 11, and so forth here. These are my 6 groups of hardware threads that are in my set here. And then my 6 MPI ranks will be mapped to those groups of hardware threads sequentially. I want all GPUs in my resource set, and I want to create this same resource set with 6 MPI ranks each on all of the hosts I have access to. So I've given it this asterisk. And so if I run this, it gives me the same output we had on the previous slide. And this is the output that it gives you if you want to look at it visually. So we have explicitly told it where these should land. Anybody have any questions about this so far? Once you understand how the binding works and how to actually define these things, it's fairly straightforward. Just a different way of thinking about it than normal JSRun. Oh, right. Here's a bunch of red text that you can look at a later date on the slides that I've already covered that just sort of explains what's happening here. Okay, so this last example, we'll look at a NPM code. So this is, we're going to use 2 different executables, and so this will give us the opportunity to look at this app option that we mentioned. So I've used hello JSRun and the job step viewer up to this point. For this example, I'm going to use a different code. And the job step viewer doesn't currently work with NPM mode, so I won't be able to show a visual output. But you have this code here, this a.c, and all it's really doing is printing out the MPI rank ID, the hardware thread that rank ran on, and the host or node that it ran on. So there's a.c, and then I also have b.c, which is the exact same thing, except down here this says b, right? Just so that you can see where the rank was reporting from is, in fact, a different executable. So this is what our ERF would look like. First, I should mention that a.c compiled into this run A executable, and b.c compiled into this run B executable. So this is my preamble up here, where I have the CPU index using physical, and where I've also set this app option. So I'm saying app 0 is this run A, and app 1 is this run B. So then I can create 2 different resource sets. Here I create a resource set with these 8 groups of hardware threads that these 8 MPI ranks will map to. This is all on host 1. I didn't define any GPUs. And these 8 MPI ranks in this resource set are going to run the first application here, this run A. And then similarly down below, I have this resource set I have these 4 groups of hardware threads. These 4 MPI ranks will have access to these 4 groups of hardware threads, and they're going to run app1, which is this run B. And if I run this, in this case, right, I didn't give it an executable since the executable is defined inside the ERF itself, and then I sort it. You can see that the first 8 ranks ran from the code A, and the next 4 ranks ran from code B, but you can see that all of them reported under the same MPI COM world, right? So they are all, although they're in different executables, you're running under the same COM world. So this is an example of what you might do in an MPMD code. Okay, does anybody have any questions about any of this? This is actually my last example before we move on into some exercises. Does anybody have any questions about the about ERFs, syntax or otherwise? Oh, thanks.
So I do have a question. So I have applications that I want to run on Summit that don't use MPI. I'm going to be using Dask. And so what I'd like to do is specify the scheduler and the Dask workers. They don't use MPI to communicate at all, but I would like to specify using ERF, the resources that they use. Can I use this syntax as ERF and not use the MPI ranks at all to actually handcraft specifically the hardware resources the scheduler and the workers are going to be using?
So this should work for processes in general, not just MPI. The MPMD mode, I don't know exactly how that would work, right? But yes, in general, those are processes, which is why I tried to use that terminology instead of MPI ranks. Any other questions? Anything remote missing? Okay. So I think this is going to end. I'm only sharing PowerPoint, so let me see if I can. Stop sharing that and maybe share my whole screen. Really, I'm just pointing to where these exercises are if anybody wants to go through and try some of these. So in this advanced section, both Chris and I have a markdown file. So you can look at the multi-JSRun exercises MD, and there's some exercises to follow along with the multi-JSRun presentation that Chris gave. And you have this ERF exercises. And so you can see in here that there are some exercises that you can sort of test your knowledge on this, right? We talked about the syntax. We looked at some examples. That helped to sort of solidify it a little bit, how you actually define these. But if you wanted to try to better understand how to use these, make sure you understand this, then you can run through some of these exercises and actually create these ERFs yourself. So for instance, you can have a setup like this where it shows the actual image. And then I sort of explain what's happening in the image, and you need to create the ERF and run it to give you the same output. And so the first 3 of these you can run just under job step viewer if you want, which is what I would recommend. Just module load job step viewer, and then create an ERF and run it under that job step viewer. And see if you can create this same image that you have here. The last example is a MPMD example or exercise. And so you would need to use like hello JSRun or JS task info to try to run this one, since, as I mentioned, job step viewer doesn't currently support MPMD mode. But if you wanted to run this last one, as it says in the example, you can use that same example I just showed previously. Those 2 codes are available for you. So actually, if you look under examples, these are the examples that I ran in the slides. So if you wanted to play with any of those, they're available here, including that MPMD example here. And then if you really wanted, you have the solutions to the exercises as well that are available in this hidden directory here. So you are welcome to try some of these exercises. We can help you either through Slack or the WebEx chat if you have questions and you're participating remotely, or if you're in the room, we can help you personally. So with that, I think we will transition into our hands-on session now.